I'm Jeff Ducklow, and I don't have nearly the experience as many of the previous presenters do. I've captained a couple of flights and been a crew member on a couple of flights, but I've been in spirit on a lot of flights on APRS, watching them. But I had an idea. I'm looking forward to the upcoming total eclipse that's going to be happening in 2023, and been thinking about photography above the clouds. And so I've been thinking about how to create a no-spin or a low-spin platform for in-flight photography. And it might be useful for other experiments that are looking for a fixed orientation as well. So perhaps there's some value on some scientific experiments that people are thinking about. But my aim is to reduce the camera aim time. So I've been thinking about this as two pieces. And I just kind of set some goals for this. Try to get a system that's less than 500 grams. And so we're no longer talking about pico balloon anymore. And try to do it with parts that are under $100. And I really would like to have a spin control system that's completely separate than the primary payload box. And sure be nice if we could get spin to practically nothing. So anyway, those are some upfront goals. As many of you may know, the total eclipse that's coming across North America will be swinging up from the southwest through Mexico and into Texas, Arkansas, Southern Illinois, Indiana, Ohio, and so forth. This chart shows historic cloud cover on April, I think it's the 8th, April the 8th, 2024. So be nice to not have clouds, but if there are clouds, it'd be still nice to get pictures. Just prior to that, there's, it turns out there's an annular eclipse happening as well.
Jeff, I'm not seeing anything but your first slide.
Oh, you're not?
Anybody else having any issue?
Yeah, he's just on the first slide still.
No,
oh,
I've been trying to move through slides, so I'm sorry if you're not
like
seeing.
You were going through slides, and that's why I was wondering.
Yeah, no, my intent is to go through slides. Shoot.
Do you have one screen or two, Jeff?
I just have one.
Oh, okay. Yeah, I had this issue on two screens, but not on one.
Do you have two versions of this open?
I may.
Because you may have shared one. You're sharing the one that's not full screen.
Okay.
You're sharing the one that shows all the little presenter ones on the left.
So are you seeing anything different yet?
Nope, we're just seeing foil 1 and it's in the presenter view, so you, or the like the notes view or whatever, so we see all your, or actually in your drafting view, it's not in slideshow at all.
Okay. How about now?
We see you on foil 2. Why don't you try changing foils to see if it, and you're not in slideshow.
I should be in slideshow. No?
No, we're not seeing slideshow. You might just need to leave it out of slideshow and go through your foils. There you go. That's slideshow. Now try navigating to a different foil. There you go. Now it's working.
Okay. My apologies. I'm not used to Zoom at all, obviously. Okay, so try to kind of recover some ground here. So trying to create a no spin or low spin platform. I'm trying to take pictures above clouds during the total eclipse. This chart shows cloud cover probability early April across the country. So if you want the best chance, you want to be in Mexico, otherwise Texas or maybe Arkansas. It turns out there's a annular eclipse also occurring about 6 months beforehand. An annular eclipse isn't quite as spectacular as a total eclipse, but nevertheless is cool. And it is also slated to go through the United States. So potentially be a good day to do a balloon flight. So these are the problems that I'm trying to solve, is how to stabilize a spinning platform and how to stay aimed at the sun. And you may recognize one of those photographs in the last presentation. That's Bill's balloon from 5 years ago. So stabilizing a spinning platform, ice skater inspiration, angular movements minimized when an ice skater's arms are extended and the spin increases. If you've ever watched a spinning ice skater, you know they bring the arms in, they spin like crazy. And measuring spin can be done with inexpensive gyroscope. And so that's my first implementation is using something called an MPU 6050, I believe. The second part of the system is, okay, once I've got a stable platform, how do I get the camera aimed at the sun? So conceptualized but not implemented is a tilt and pan unit that's driven by an Ardunio or some microcontroller and a bunch of photo array sensors across the styrofoam half dome, and simply looking for the strongest azimuth and altitude, assuming that's where the sun is. So that structurally or architecturally is your sensors plugged into a foam array that are multiplexed into an Arduino. The Arduino tells the tilt and pan unit to move the camera one way or another, and your camera has a solar filter and starts taking pictures. All of that is future. I haven't played with any of that yet. Right now, I'm focused on trying to create a stable platform. So the architecture on that is gyroscope that's plugged into an Arduino, and there's a little display off to the side. I tried doing a debug of this system without any kind of display, and it's pretty much impossible. And of course, you don't have the capability to use a serial port to your computer when you're measuring spin on a platform. So that's what the display is about. It wouldn't probably fly, but it's certainly useful for debugging. The Arduino drives a servo driver board that in turn is connected to the motor and the torque arm. So there's a picture of a demonstration box, and the torque arm is a simple stick with a couple of ping pong balls stuck on the ends and a couple of plastic anchors that protect my eyes from being poked out, and all kind of tied together with some string so we can do some testing. Here's the inside of the box. So all the pieces that I just described. And there's the little display that gives me feedback on what's happening. Here's another shot of the torque arm. It's about 3 feet in length, and one of the subtleties of this is connecting the stepper motor to the torque arm, and discovered these so-called soft couplers. They've got flexibility so that you can have quite a bit of movement on your torque arm and still retain quite a good physical connection. Whoops. Uh-oh. Oh, crap. So at this point, we maybe share the link. Mike, can you throw that up on the chat area?
If I had it handy, I would. Give me just a second here.
I got it, Mike. Just posted it.
Excellent, thank you. I just found it, but hadn't got there. Oh, and we also had a question in the chat just before that. What makes the payload spin?
Well, the physics of you tying a box to the bottom of a balloon, you're likely to spin left or right quite a bit just because you've got an unbalanced system. So if you all would jump to that YouTube page and watch the video, you'll see the box in implementation. So it's about a minute and a half video presentation. Let me know when you've seen it.
I'm just starting it. It's taking a while to load here.
So go ahead and click on yes in your participant window when you're finished with the video.
All right. So hopefully most of you are now seeing the hardware materials chart.
Yeah, we're not in presentation view again, but I don't know.
Oh,
Just hit slideshow and see if we see the right one. Or try moving just to make sure it moves when you try.
you see a software flowchart?
Nope.
Oh, shoot.
There we go.
So the video showed two demonstrations of the box. One was without any load, any kind of weight on top of it, and the second was with about a pound and a half of water on a container. And in both cases, it did kind of settle it down, as you saw. This chart is just basically an outline of the software that's driving the Arduino. So if you've done some programming, you know, on the Arduino, there's a setup section where you're initializing hardware and setting a reference direction, setting up a timer. And then there's a loop, and the basic outline is you know, look for a change in the yaw, in the spin, and which is it counterclockwise or clockwise, and then calculate how much time has gone by since the last time you did a measurement. And with that, you can calculate an angular momentum, a spin rate. If you're stable, hey, go take some pictures. Otherwise, fire the stepper motor proportional to the momentum that you measured, and loop back and rinse and repeat. So I have the code on GitHub for anyone who would like to take a look at the code. It's certainly open to if anyone really wants to dig down into it and collaborate with me. I'd certainly be open to that. Let's see. There's some libraries that I'm pulling up, and give credit where credit is due. I pull information or pull library from Adafruit to drive the TFT display, and a guy by the name of Brett Stratham created a stepper motor control library that I'm using. And then the gyro gyro itself has a library. Jeff wrote. Of the event. So
Hey, Jeff, your audio is breaking up. You might just stop your video feed to see if that clears up your audio. Leave your screen share up, but just turn off your video to your camera.
okay.
Or just try talking now. It might have just been a real brief issue.
All right.
You sound better now.
All right. So. So are you all seeing a chart called implementation?
Yes.
So as implemented, it's about £1.50 pounds, so it's kind of heavy. I spent about $85 on the electronics and $10 on putting the box together. I've not flight tested this at all, so it's all ground tests. It's about 50% faster it stabilizes 50% faster than if the box isn't running at all. In other words, with the system off, stabilization occurs in about 60 seconds or so. And with the system on, stabilization occurs in about 30 to 40 seconds. So it's not great, and it certainly isn't up to where I'd want to use it to orientate a camera, but it's a stab at it. I have my own kind of standard payload box that I've used to fly with, and kind of like the form factor of it. And so there's a picture of it, and then with some crude graphics of how I visualize how I'd fly down in the future. So that spin stabilization unit would be tied into the bottom of the box using, I found PEX waterline is real lightweight, and super strong, and super cheap. And so that makes a good structural connection. And then as the camera system itself comes together, I visualize that sitting on the top of the box to have free access to move 360. So there's design limitations the way I've implemented this. The swing arm can be awkward, and frankly, it's always in the way. It's sticking out the sides of the box. The whole thing's fairly heavy. The batteries don't help. I do I do know that I could substitute lithiums, and they take out some weight, but it's in my view a little bit heavy. I used a really inexpensive stepper motor called a byJeff, and it's low cost. It's $4 or $5. It's low weight, and you can drive it with 5 volts or 6 volts. And so all those things are nice for trying to create a lightweight system, but it's slow. Top speed is about 7 revolutions a minute. And so that's a real limitation to move that arm around. Some ideas for getting out some weight is, obviously take the display off for flight. Potentially use a smaller version of the Arduino, although, as I pointed out, I'm already using quite a bit of the memory. And there's all sorts of little things, substituting metal parts for nylon parts, potentially using a carbon rod. There's a little breadboard in there that could be taken out. And then there's something that's really kind of a major issue, is this GPS unit that I picked locks up quite frequently. And there is something as a well-known issue called gyroscope lockup. It happens in mechanical systems as well as electronic systems. And in fact, the Apollo 13 movie kind of had a side drama of if gimbal lockup is going to happen or not, if you might remember that movie. You can detect when your Arduino is not operating, and with using something called a watchdog timer. It isn't foolproof using that as a solution. So more work needs to be done, possibly using a different gyroscope detector that's not as susceptible to lockup, or who knows, but this is an issue. So, and because we haven't flight tested it, just thinking about, okay, what can go wrong? Well, that stepper motor could lock up because we get too cold. The cheap motor fails after continuous operation. I mentioned the watchdog timer not always solving the MPU lockup. And potentially either the parachute or the balloon itself gets entangled with the torque arm. So things to think about. So this kind of shows a proof of concept. Yeah, you can kind of get your box stabilized. That the gimbal lockup is a real issue that needs to be solved. There's probably other faster de-spun methods that could be implemented. Listening to the first presentation this morning, it sounds like potentially a disc on a motor might be a better way to go. And there's probably other people that have thought through this that have solved this problem before I have. But I'm certainly this is a shot that I've given it. So if I'm going to go forward, I definitely need to test the whole system integrated together and develop the real camera aiming system. So a lot of work in front of me, but I thought we'd present what we had and get some feedback. So with that, certainly open to hearing questions or discussion.
Hey, Jeff,
Okay.
question. Do you have a garage or anything like that that you can do your testing in with like maybe a high-powered fan? Kind of like set up a wind tunnel test is what I'm getting at.
Yeah.
Okay.
Yes, I do have a garage, and yeah, I thought about testing with a fan as well, but have not done that.
Okay. Well, let me just give you a couple of suggestions. I fly for a living, and we got rudders on airplanes for a reason. So if you can test with a fan blowing again, you're going to get the spin because the string coming down from the balloon is trying to find an equilibrium. And there's a thing called stability, positive dynamic and negative dynamic stability. If you want to read about that, it's in some of the tests that pilots have to take for their, as they advance through the piloting stuff for their different certificates. But with one string coming down from a balloon to hold the box, there's a lot of that in there. It's trying to find an equilibrium the whole time that it's up there. And that's why you'll see these pictures going way out to the left and way out to the right. And they keep going backwards and forwards. Like somebody said a while ago, it's the vomit show is what you get with that. A couple of things you could probably do, like in your box here, you've got 4 strings coming up. If you can put like a cross up there just below the balloon, you still have the parachute above it, but kind of cut down on that swinging, because the more you cut down on that length of line, that equilibrium will probably balance out. But if you put an arm on there, kind of like a rudder, instead of one on both sides, and experiment with it, with the wind blowing at it, normally when you take a look at the farmhouse and it tells you which direction it's going, you got a pointy arrow on one end and you've got like a big rudder on the back end. And you could probably point it into the wind and then have that stabilize off of it being pointed into the wind with a shorter, string, so to speak, and support it by like 4 strings in each corner like you've got the box here, and put a rudder on it. That
Sure.
might, I don't know, it's just an idea.
Yeah, no, excellent thought.
Get in your garage and put that box about 1 foot off the floor and have it dangling about 8 feet up, and then try it with a rudder. And the other thing is, if you want to have 2 arms coming out, you can have like a flat plate and have it be able to turn each one individually to try to balance that out a little bit as a possible, just for experimenting.
Yeah, good input, good thoughts to try.
Okay,
Hey, Jeff.
just but it works. I'll get out of here and let the other guys give you ideas also.
Hey, Jeff, yeah, I've actually been thinking about this problem myself, and I went a slightly different way. I haven't played with it yet, but I saw some videos, Joe Barnard, who does rockets, and he does a reaction wheel in his rocket, and what he does is he spins up a disc basically inside the fuselage to a certain speed, And when he launches the rocket, then he either accelerates or decelerates the motor that is spinning that disc, and that puts a spin and can turn the rocket in flight. So he's actually got a rocket that he launches straight up and then turns it 90 degrees in mid-flight, which is really kind of sexy. So I was actually wondering if a reaction wheel technology where you spin it up to say 1,000 RPMs, and if it starts turning clockwise, you slow the reaction wheel a little bit by just, basically dialing down the motor speed to impart that momentum back into the payload box, or vice versa.
Sure.
So that was something I was thinking about. I don't know if you've given any thought to that.
Yeah, I hadn't actually thought about a disc until this morning when the gentleman from
I think Bill mentioned it.
India spoke. Yeah, yeah.
Well, yeah, Giant mentioned it. We used it. We had that was our semester problem for the students, was package stabilization, and so. And briefly, I'm going to talk about Mike and rocketry. A friend of mine put in the fins of his large and dangerous rocket. He had reaction wheels in the fins and spun them up with compressed air to about 20,000 RPM. And then the other set of fins could move the same direction, and he had an RC control unit. So what happened is the two reaction wheels would counter any yaw. And as it went up, it would stay the same orientation, and he could steer it this way, back and forth, with the other fins that would move with the RC. So they work great. And so what we did when UAH, for package stabilization, they used a big reaction wheel to counter it. The problem is their system weighed like 3 or 4 pounds. It was pretty heavy. It was almost at our weight limit, because we always have a weight limit of 6 pounds for the student payloads. But it actually worked pretty well. One put 2 ducted fans out about 3 foot on either side of the payload, which worked great in the troposphere, but when it got in the stratosphere, it didn't work too well. Another group used, remember the Gemini little gas unit that they used to steer themselves around in the spacewalk? They had 2 gas jets coming out. So one group used CO2 cartridges and would try and do a gas jet stabilization, but of course there's a limited opportunity for that to work until you run out of the CO2 compressed air. So that actually worked somewhat, but it couldn't handle big swings. So I put together a package with 6 foot of carbon tubing out on each side, with exactly like you had it, with the big styrofoam balls on the end. They act, other than keeping people's eyes safe, it also adds a drag element to your rods. So it's useful to have those balls on the end. And it was rock stable. And I told the professor I was helping out, I go, do I get an A? He said, write a report first. But it was just like an elevator. It's like a tightrope walker's cane. It has that effect. So I love what you're doing here, and I think it shows great promise.
Well, thanks for the encouragement, Bill.
Wouldn't a couple of lead weights be better than styrofoam balls? That'd give even more inertia.
Well, now, way back 28 years ago, what did he call Chuck Chris flights? Mark, what did he call that? Wind tracks. He put a bar off about a disc with holes punched into it, big 1-inch holes in it. The disc was about 1 foot in diameter, and he put it off horizontally so that the disc was up and down as a drag element. And if you got it right, it worked. It prevented spinning quite a bit because it created a lot of drag on one side. What we did for the Eclipse that I mentioned earlier, we had the two of those solar sensors divided by a black plate, so that both sides had to see it to be pointing at the sun. Of course, we were near the horizon with that. And then in the other side, we had a rudder because we're flying up, right? So the rudder adjusted the, as long as you were continuing up, the rudder steered the payload to keep the both sensors illuminated. It was a closed loop system. We actually really didn't have a microcontroller in it at all. It was just an analog closed loop on the rudder. And that worked until the sun went out.
What I've experimented with this system is actually adding clay next to the ping pong balls to get some more mass out there. But the
magnetorquers is another option. If you're floating, for example, the magnetorquers might work in the stratosphere. But there's power penalty to be caught, you know, for doing a magnetorquer.
I don't remember who, but at some point somebody recommended hanging flags out at the ends, so you get to use the wind to do a little dampening.
Well, that's what we did with the rudder. It was basically a styrofoam foam core flag. But yeah, it really helped. It really worked great until our sensitivity on our solar sensors, our light sensors, weren't enough to handle a total eclipse. But your system with the hemisphere, you'll still see a light difference with the corona of the sun if they're sensitive enough. But just be aware, it's going to be only a fraction of full sunlight. So make sure that it can handle that total eclipse phase.
Sure.
Jeff, I really like the reaction arms being active. That was kind of neat, new concept for me. One thing it's not going to fix your problem by any means, but don't forget to rotationally decouple from the balloon. You know, put like a ball bearing swivel up above your payload to keep any of that winding up of the load line decoupled, and any twisting of the balloon itself, keep that decoupled from your payloads. You're not fighting that the whole time.
Yeah, you're not seeing it, but I've got two swivels up above where the strings are coming together. One of the things I'll mention is I did try adding weight out where the ping pong balls were to see if what changes would occur, and you know, the extra inertia of that weight kind of balanced out with the stopping ability of the of the torque arm, and so it kind of was a wash, and you're adding weight to the whole system. So at least in my experiments, adding weight at the end of the torque arm was not helpful.
Well, looks like it would be sturdy enough, doesn't it?
I'm not hearing.
Those books.
The added drag of those foam balls will help. Now, EOSS, they fly on their camera payload. They just have carbon fiber.
Get a lot of stress on it if it drops.
What's that?
Sorry.
They have poles, fiberglass, and carbon fiber poles on either side. I don't know if they're 6 foot on either side. I think they might be 3 foot. And even the 3 foot poles on EOSS camera payload seem to really stabilize it.
Jeff, one of the things that I tried was a drone flight controller. It was called a KK2, and you can blow different firmware to it to where it does not take RC input, but you still have yaw and pitch on the output, and it worked. And we got some good pictures. Now, if you could couple that with your sun sensor, you would, and I just made a simple gimbal and put a little Mobius action cam on it and had it in a box with that KK2 flight controller. It's called KK2 flight controller. You might look at it. It's got an Atmel. I think it's got an Atmel processor. It's got gyros and all kinds of stuff on it.
Okay, thank you.
And I also mentioned there was we did some flights 20 years ago for Wayne State University, and a professor there who was also ham. I flew a sun tracker, and he was trying to characterize space qualified cells by pointing the cells at the sun. And he had a very similar gimbal arrangement like you're planning to do. And he could actually track the sun with 2 servo motors on this solar cell sensor. And but we did that 20 years ago, and I'll have to find his, I'll see if I've got some old photos of that somewhere.
Oh, that'd be great.
Okay, I think we're probably at about time for this one.
Thank you.
Thank you, Jeff.
Okay, so our next speaker is Mark Patton, KC0D, and he's going to speak about an ADS-B payload that EOSS is in the, I'm not sure if they've flown it already or whether they're about to, but I guess it'll be interesting for potentially keeping air traffic control informed of where our balloon flights are going. So go ahead, Mark.
Standby 1.
I was going to say you're not in presentation view either, so just wanted to make sure that you were aware of that. There it is. Fastest talk ever.
Mark, you're on mute.
I hope you all got. Yeah, thanks. I could. Turns out I can't unmute if I'm in full screen or something. I don't know. That's all right. Now, let's see if this works. Okay, is it in full screen? Can you see it?
No, it's not.
It went to the other monitor again. You know what we're going to do? We're going to say, heck, can you see the, how's that?
That looks fine.
Okay.
That'll work.
We're going to do this because the other one, anyway. Hi, I'm Mark Patton and KC0D with Edge of Space Sciences. And as Mike said, I'll give you a little bit about, we got involved with ADS-B, kind of drug into it in a way because of some of the heavy balloons we fly and some of the experiences we've had. So with not being able to fly due to cloud cover. So first of all, I know we have a lot of people who are pilots out there. So I'm not the ADS-B expert in the group, but I thought for those of you that don't even know what it is or never heard of it, I'd just give a real quick explanation. So this is a technology that the FAA has moved to, and as of January of this year, it's actually a requirement for aircraft. And so it's a digital transmission. So if you have like 2 airplanes, they're transmitting their position, altitude, direction, speed, position, information, not only to the FAA down here, to receivers that the FAA has, but to other aircraft. So they're using the GPS and, oh, I should bring up my little pointer here. Let's see if I can bring up the annotation guy. Otherwise, you're not going to be able to see it. Spotlight, laser. There we go. So they're using the GPS up here just like we do. But there's also these comm satellites. So that could be Global Star or Iridium satellites that they're actually picking this up. And then going down to companies that offer this as a service. Also, there's a bunch of people, just hobbyists and so forth, that have receivers on the ground like us, who can receive and put this all up on the internet. So I guess to note is this internet thing over here is not associated with what the FAA is seeing. They've got their own receivers. We can't see exactly what they're seeing, but we have our own receivers, and we can see, we should be seeing the same thing that the FAA is seeing. What this does, and one of the reasons the FAA moved to this, is because now the aircraft can see other people who are around them, who are threats, who are ahead. The FAA can increase safety because they can close in the spacing of aircraft and so forth. As well as if an aircraft gets lost or someplace, the satellite link can find out what their last position was or where they currently are if it's still working, and be able to find them more quickly. Okay, so our motivation was, as I mentioned, we fly these heavy non-exempt flights. So we'll fly a 3,000 gram balloon with 20 something pounds, over 20 pounds sometimes, of payloads on it. Looks a lot like this over here on the right with all the student payloads on it. University of Colorado, sometimes we'll fly 2 3,000 gram balloons with all of these student payloads on it. And so it's a big class and a busy day for us. And so with that, we can't fly over 5/10 cloud cover. So what happens is we get up in the morning, looks good, drive out to where the launch site is, which is usually an hour and a half away, get out there, and guess what? It's cloudy. And so if the clouds aren't going to clear, then we end up having to do something bad, and that is we have to reconfigure the one 3,000 gram balloon to 2 1,500 gram balloons. And as the math works, two 1,500s don't all hold the same payload weight as 1 3,000 because of overhead and like extra payloads that we use and so forth. So that means that some student payloads have to be left behind if the balloons are fully loaded, and most of the time they are. So now suddenly our TNR teams have 2x the number of balloons to chase. So if we're flying 4 1,500s, we've now got 4 balloons to chase, and we may not have enough trackers out there to chase all 4. So this is just a big problem. We've had times where we've had to actually come back the next day, and it's a big pain. So our goal was to be able to fly without, regardless of what the cloud cover was like. And so we thought, well, maybe if the FAA could see us and the other aircraft could see us, maybe we could still fly. And we looked into ADS-B, we found out, well, the aircraft, if they've got the ADS-in capability and be able to see the other aircraft, they can see our balloon, the FAA can see us, we're good, we should be good. So, and as I mentioned, this was required on the aircraft starting in July 2nd. So our plan was to look into ADS-B, how much do these things weigh, how much power do they consume, if they're a big heavy duty transmitter and they weigh 35 pounds and they cost $15,000, we're not going to probably be able to fly it. But maybe some combination of this, like they're inexpensive, they don't consume much power, and they weigh a few grams or something, we could fly it. So we started looking into that. So he said, well, okay, if this is feasible, what's our plan? So our plan was to fly the ADS-B regularly over a period of a couple years in coordination with the FAA. And by that, I mean, we would let them know we're flying with ADS-B, what the call sign is when we file our paperwork with the FAA, our highball and so forth. Log a whole bunch of flights so that the FAA starts requesting us to fly the ADS-B. The advantage for them is they can see where our balloon is. They can steer aircraft around it. It shows up right on their screens with the other aircraft. So it's a great solution. And then once we have that, approach the FAA about modifying the waiver to see if they would let us fly through clouds. Because unless you have ADS-B, unless you can see what you're doing, you shouldn't be flying through the clouds. So VFR is a no-no. So the University of Colorado Space Grant that we fly all of these for was very interested, and they said they would invest in the ADS-B transponder. So what we found was a company by the name of U Avionics has these small ADS-B transponders, and this guy weighs 76 grams. Okay, so that met our requirement. It's targeted to commercial UAVs. They're flying maybe around airports or something, because they have a requirement that they should have ADS-B. FAA would really like them to have it so they know where they are. It was claimed to work to at least 70,000 feet. And I believe that the limit there was really the barometer inside, not the GPS. It has a barometer inside for reporting altitude. The altitude reports as barometric. It's not the GPS altitude. Well, but actually it turns out that it actually does report both, but they really use barometer for altitude reporting. It has a dipole antenna that you could get as an option, which is a little short little guy, probably about 6-8 inches long. Runs 11 to 33 volts, 2 watts average. Now the interesting thing about this is this guy transmits with 250 watts, but it only consumes 2 watts. And that is because these transmissions are very short, like microseconds, like tens of microseconds. And it uses the 1090 megahertz on the transmit. The downside is it costs $4,000. So, you know, you have to have a custom, either you have to have deep pockets, a customer who has deep pockets, or yeah, or something, be willing to invest in this thing, and then hope you don't lose it. So as I mentioned, the University of Colorado decided this was important enough to them that they would buy one of these. And so then we started through the rest of the process. So having the transponder is one thing. You need a call sign. So now you're an aircraft. So they went through the process first. They ended up getting their legal department involved. There's a really difficult process that turns out is not so difficult if you know what it is, but there really are no instructions. And if you want to go down this path, contact Marty Griffin, WA0GEH. He's our guy for getting call signs. They're free from the FAA for the application. If you want a quote vanity call, that's $10, and that's where you apply for a particular call sign that's not used, kind of like the ham vanity call signs, and then for $10 you can get your own call sign. That's what we did because we were kind of particular what we got. With that, when you get your license, you get what's called an ICO code. It's 6 hex characters. It's derived from a number the FAA gives you. Unfortunately, they don't tell you how to convert the number they give you into an ICO code, but people know how to do that. I know how to do it because I figured it out. Or you could just look it up on the internet once you get your FAA call sign. You also need to put in a squawk code, and what we use is 4453 for high altitude balloons. There's a whole bunch of these for different things, and we recommend if you're flying a balloon, you use 4453, because then the icon on the screen changes to a balloon. Everybody knows it's a high altitude balloon, and you're good to go. Okay. Now, the other thing you need, we found out, is an ADS-B receiver. And the good old Raspberry Pi works great for that. You load up one of these operating systems, you get yourself an SDR like this. The FlightAware SDRs work well, so does some of just about any of them. A 1090 megahertz antenna, which looks like this on the right, little short guy, mag mount. The software that runs a program that's called Dump 1090. I think that's because of the frequency. FlightAware, which is called PiAware for the Raspberry Pi, is the one I use, and it works great. And it's all packaged up. You just follow the instructions, download it, and it just works. And then I use grep on Unix to log the packets for our balloon, because what comes out of Dump 1090 is everything it hears. And you can be getting like 2,000 packets a second. So it quickly overwhelms many things, including any way you try to capture it. So what we do is we piped it into grep, grepped on our call sign, and then redirected that into an ASCII file. And that works great. So what FlightAware screen looks like, this is an example in around a major airport. And so you see all the aircraft lining up to come in and go out. They're color coded by altitude. You can type in some filters up here. So if you want to filter by altitude, you can do that, which is real handy for high altitude balloons if you don't want to look at all the other aircraft in the sky around you. You can also, I found out that if you squawk the right high altitude balloon code, you'll appear on here as a balloon. Over on the right is a flight we flew just a couple weeks ago. And this was the ADS-B. This is off of my iPad. And this is the launch. It goes up, makes this S-shaped curve, and this is supposed to be a balloon at the end. Looks like an upside down balloon, kind of. But you can see over here, it'll give you the altitude and so forth on the screen, which is real handy. And again, if it's up above the aircraft, like above 50,000, you just load this up for 50,000 feet and you're good to go. So what happened was, is we loaded this guy up, ran 6 flights last year with this, and we had a consistent problem. And this is one reason you want to have your own ADSB receiver. We were trying to look at stuff off the internet, and we kept seeing that the balloon would go up really well, and then all of a sudden we started having problems around 57,000 feet. It was coming and going and not appearing, and it was gone. And some of the web pages, they filter everything above 50,000 feet because nobody flies up there. And so anyway, we decided, okay, we got to cut the problem in half, get our own ADSB receiver, and that really helped us narrow down the problem. So these on the left, this is the packets with altitude that we received, and you can see that it's kind of thin over here on the right. But if you look at the packets with latitude and longitude, it goes up to 57,000 feet and it just quits transmitting. And then it picks up at 57,000 feet on the way down again and follows it all the way down to the ground. Well, that isn't right. So finally, after 6 flights, we decided to contact the manufacturer. They looked into it. I said, this is supposed to be good up to 70,000 feet. They said, oh, we know it works. And so they looked into some of the data they got off the FAA website that they have access to. And they determined that their unit was defective. Not defective, the whole series of them was defective. Evidently, they swapped out GPS units, and it wasn't, we've all had that problem with GPS units. It wouldn't give them Latin long above about, in their case, it was 57,000 feet. So they sent us a new unit. This was an experimental unit. This one's called a Tail Beacon X. This is intended to go in the back of an aircraft where the tail beacon is. And beacon it's really the position light. It's really not a beacon. So this replaces the position light in the back of the aircraft with these 2 little wings, which is the dipole antenna sticking out the back. And then it's got a light built in. The one they sent us, we asked them to disable the light because we don't need a light, and which saves us about 1 watt in power. So same thing, it's got the same thing built in. This one's 1 watt higher in power consumption because of the LED light. It weighs 90 grams instead of 75 due to the extra antenna and the plastic around it. They claim it's space-based ADSB compatible. I don't know if that's anything special or just marketing. The good news is the price on this one's $24.99 for the experimental model versus $39.99 for the other one that doesn't work. This is what it looks like. This is how the students packaged it up. They mounted the unit through a piece of Kydex, which you could barely see in the background here. And then the battery pack is up here in the corner. And then they just fired up. This is the through tube that the flight string runs through the center of the payload. It measures about 6 inches by 6 inches on the side. Fully with the batteries and everything, fully packaged up, ready to fly. It weighs about 485 grams. This is the N number and the ICO code for this particular unit. We're going to be flying this tomorrow, so if you've got nothing else to do or some special extra time, go on the web and you can look this up, and that will be us flying. So we've only flown this unit once so far because COVID hit, and tomorrow will be our 2nd flight. And so, but the first flight, the problem seems to be solved. We were able to get altitude and position reports all the way up to about 78,000 feet on this particular flight when we had to cut it down, and then you know, on the way down. So we think the problem is now resolved. Couple of comments, and that was from the FAA. Has been very good to deal with. We were open with them what we were doing when we were having issues. They actually sent us their ADSB and radar data, and which I was really fascinated to find out they could see our flight string on radar, which I didn't really think the radar was that good, but evidently it is. And so they sent us that, and now they're asking, you know, to make sure what our call sign is and so forth when we're starting to fly, because they really like this. We've also heard some comments from pilots when we had a flight where we had one of our guys in a plane that was flying around with Metro State University, and they were listening to air traffic control. And we had some commercial pilots. Well, we heard the FAA steering them around our balloon, which was really good. But some comments from pilots were that because they knew it was a balloon, that they were able to see it up above where they were. So that was fun. So, we're going to continue to fly this. When we get our good body of evidence, we'll be approaching the FAA and see where that goes. But we will probably be getting 1 or 2 more units so we can fly on a cloudy day. We could, we have to fly 2 or more ADS-Bs. If as many balloons as we have fly, we have to have ADS-Bs. So maybe acquiring one of our own, or CU may decide to acquire another one. So questions for me?
Yeah, Mark, I have one question. You said that the unit that you initially started testing with is one that's now required in commercial UAVs. And it sort of ties into, I'm a Model RC plane guy, and I know that the FAA is pushing for remote ID.
Mm-hmm.
And they've pretty much proposed a solution and said, okay, here's the problem it solves. Now tell us, what you think of our solution. And I can tell you, I'm not real excited about remote ID. I think it's putting a lot of burden on amateur, RC pilots. That said, I'm a little concerned that if FAA gets pregnant on this solution for ADS-B and high altitude balloons, could this turn into they slap remote ID on high altitude balloons and put this kind of requirement for a $4,000 device in everybody's balloon? Do you guys thought about that at all?
I actually hadn't. We were mostly concerned about the issue of flying through the clouds. But you're right, if they were to get very well, not only for our balloons, but the Google's been flying their loon balloons all over the place. And if you go to these sites and you put the filter on for like above 50,000 feet, you can see where the Google loon balloons are. And they're flying those, of course, all over the world. But they are flying ADS-B in theirs, and they're clear up at 50-some thousand feet where they wouldn't have to.
Mark, can I add something here?
Please, go ahead.
The requirement for ADS-B is not just commercial. The requirement for ADS-B is on any civil aircraft that is operating in what is called and defined as controlled airspace. So if you're flying within 500 feet of the ground with radio controlled stuff, this regulation doesn't really apply to you unless you're in an airport traffic area or a Class B or Class C airspace. So we happen to fly through that kind of airspace naturally because we're so close to Denver International. And once you get up above 10,000 feet, it's all controlled anyway. So we live in controlled airspace with high altitude balloons. With radio controlled stuff close to the ground, you really don't. But there is a requirement, and it applies not just to commercial, but to all civil aviation flying within controlled airspace. And that was as of January 2nd.
Well, remote ID is going to put that requirement on all model aircraft as well. So that's why we're pissed about it.
There is no such thing as uncontrolled airspace. Ask any flight instructor and he'll tell you all airspace is controlled.
That's true.
Well, Class G is considered
One of the things, sorry,
yeah, I'm sorry. What's your N number going to be so we can look it up on FlightAware tomorrow?
John, do you remember what is it?
It's the one that was on the slide. It's the
Oh yeah. I'm sorry. Yes, we're not flying our call sign. We're flying this.
Yeah, N461 Sierra Golf.
Yeah, it stands for Space Grant.
N461 Sierra Golf.
Yeah, and write down the ICO number as well. It's A59 Echo 9.
Echo 9.
Yeah, A59 Echo 9.
In response to the other guys' stuff, I do some RC stuff and I do commercial flying also. Yeah, that's going to be an argument you're going to see come up in the future, but you're going to be able to counter that with there are 500 weather balloons launched every day by the weather services around the world. It's going to be hard for them to justify $4,000 per balloon because they do 2 balloons a day at the weather stations, like in Little Rock does it at like 5 a.m., AM and PM, and the other ones do it too. So that's going to add an awful lot of bigger cost on that.
Those are exempt from FARs because of weight.
Yep, true.
We are not exempt because of our weight. That's our problem, is when we fly non-exempt with these 3,000 gram balloons, we are subject to all FARs. The weather balloons are not.
Okay.
Yeah, that's really where we got into this, is because of the non-exempt nature of what we wanted, of what we're flying for CU.
So
Yeah,
allow me to
I
talk out
just-
the other side of my face for a minute.
Okay.
I can take both points of view. Remote ID, which they called for feedback, but they don't want feedback. They're going to require remote ID for remote RC airplanes. Is it possible, or do you have anybody looking into whatever hardware, and maybe it's all vaporware now, but the remote ID hardware, if they do have to mandate it for RC airplanes, it's likely to drive the cost down really, really cheap. And so the question would be, is the remote ID stuff that we are going to be mandated to use in RC airplanes, could that potentially be used for high altitude balloons? Now, I don't know. Yeah, obviously, RC airplanes are supposed to be under 400 feet, but it's something else to think about.
Well, one of the requirements, if you look through the requirements now, the reason that this one that we're flying right now, this Tail Beacon X, the reason it's experimental is they're just waiting for the FAA approval for this unit, and they're going to raise the price of it once they get the FAA approval. They've already said that, like $500 or something like that for the approval. But one of the requirements is it has to transmit 250 watts to meet that requirement. I can't imagine them requiring you to put a 250 watt transmitter on an RC airplane.
I think the RC stuff ends up going through the internet. So yeah, that's probably
okay.
a non-starter. I thinking out loud there, and you're right. I think the RC stuff, I think their transponders are going to end up linking to your phone or something, and then they upload to the internet, and then the FAA gets that data that way, so they know where all the RC planes are on the ground.
Yeah, it seems like
no one understands.
I was going to say, it seems, unless you're flying next to an airport, who cares?
Hey, Mark, can I add something?
Sure, go ahead, Marty.
So we understand your situation, Mike. The FAA is twirling around and working really hard on coming up with some new rules with what they call UAVs, with whatever definition they have. And twirling is not a bad term for it, because it's certainly not like they're well grounded in what they know. But this company that we're dealing with here, their entire company is based on UAV work and drones and all that type of thing. That's their market. So they probably would help us or benefit us with lower prices at some point as the market for their products increases. So let it be known that EOSS and the quasi lawyers that we have as members are very, very sensitive to this discussion of new rules and such, and very much in tune with what's going on. So we're not going to, we're going to make sure that nobody gets hurt on this as far as our actions are going. So we're sensitive to that, Mike.
That's an excellent thing from somebody that does both sides of the aviation world. Where every time I go up to New York, I get nervous when they announce that there's a drone flying around, and people are out there with lasers that they buy from the dime store. So it's the people who gets the cheap toys that go out near the major airports that's causing all the problem for everybody else. And that's what's going to, if they bring down one airliner, I guarantee there's going to be crazy stuff, falling all over everybody, whether we're, trying to do it legally or not. Just because people out there that don't have the brains to do what they're supposed to do or not doing it legal, that's going to cause a problem for everybody if that does ever happen. So anyway, I see both sides of that. When you said speak out both sides of your mouth, I see both sides of that argument, because that's certainly dangerous when you go to some of the world's most busy airports around New York and somebody's doing stupid stuff like that. So anyway, appreciate you guys and what you're doing. It's a great presentation.
One other thing, Jim just brought up a good point. On the last flight, when I showed you the picture from my iPad, this was not the same ADSB that I'm showing here. This was one from NOAA. They were flying an ADSB in theirs, and it was the same ADSB. It was just a different call sign and so forth. And we told them at the beginning we were flying ADSB, and they had some problems with it, and we don't know exactly what happened. They had the antenna oriented sideways and some other things, and it was first time they'd flown it, and who knows. Anyway, the FAA had it for a while, then they lost it, and they made 4 phone calls to our ground station asking, "Where's the ADSB? Where's the ADSB?" Because they had seen it, then it disappeared, and they knew it was probably in their flight space. So they're going to get quite accustomed to this quite quickly.
I have a question, Mark. Mark N0NQN mentioned that FlightAware is one site to track. Is that what you primarily use as far as an internet tracking site, or do you have any other sites that or apps for phones that might be useful?
Yeah, I use Flight Radar 24.
Okay.
I don't know why I use that one. It just seemed, I just like the interface into it. FlightAware is one of them. I think there's at least 2 or 3 different ones that have interfaces for phones. Flight Radar 24, I know does. And
I've used that one.
Yeah, I've used that one. I know works on a phone. It works on the PC.
And what power, what size batteries do you use to power this unit? Because that, or do you have super caps on it to handle that peak?
No, well, the peak current isn't very high. I think that the caps are built in.
Oh, okay.
For that. And the peak is only, it says 2 watts average. We were concerned about that. I haven't actually got my hands on it to see what it's actually transmitting or what it's actually pulling out of the battery. CU, when they package this guy up, you can see it up here in the corner. I don't know if you can see it very well. It's a black battery. It's like a UAV battery.
Wow.
Up here in the corner. So they've got a battery that's much bigger than it really needs to be. But they've run this thing like for an entire day and it's never run the battery down. So they don't really know how long the battery lasts yet.
So is that like an RC airplane LiPo pack of some sort?
Yeah. I don't know if
probably have to be 17 volt. Probably 14 volt pack.
I think it's 14 volt. Yeah, because the requirement has to be between 11 and 31.
Yeah, and the 21, at least 2100 milliamp hour.
Yeah, it's at least that.
You can see the balance plug sticking out of it. There's 4 wires.
That's right. That's this white.
Yeah, that's the 4.
So that would be wouldn't that be a 3S? Because ground and 3.
Yeah, 3S.
That's a 3S.
3S, yep.
Okay.
And it could be, it's hard to tell what the milliamp hour rating would be because I've got many of those from 1800 to 3400 milliamp hours. So.
When they were trying to, so the first version of this I mentioned back here with the first ADSB was really heavy, and I couldn't figure out why it was so heavy. And so when when I got involved with them, they were just we were trying to figure out what was wrong with that one, and they hadn't gotten this one or packaged it up. And when I was talking with them about packaging up, I found out they were using masonite in this thing to hold that, to mount that on. I said, masonite, really? Have you ever heard of like Kydex or something that doesn't weigh like 2 pounds just by itself? So that's what this was mounted in. But they were trying to lighten up the battery, and they found out that the batteries were about the same weight, so they just went with the one they had.
Somebody asked a question about what the weight is for exempt, and when you're multiple packages in a payload string, I believe that number is 12 pounds. Does that sound right, Mark? For exempt versus non-exempt?
Yeah, sounds right.
Yeah, I had to file a waiver for a 15-pound payload I sent up for a NASA group 2 years ago, but that was before the rules in January, and it took about 2 or 3 months to get all the paperwork put in place. Plus, we had to have a dedicated person coordinating with the local air towers and the FAA centers.
So we have a waiver that we file once a year, and we tell them all the launch sites we're going to be using, possible launch sites, and then Russ Chadwick is our FAA guy, so he files the highball and the paperwork with the FAA several days before the flight. And
ours was good for a year, but we had to extend it by 3 months, and they did extend it, but it's good for a year. Is when I got it.
There you go. Okay.